Any questions about anything? About anything? Well, today I'm going to talk about the complex version of the inverse function theorem. And complex, of course, meaning complex numbers. I'll also talk about what I to the I maybe should mean. It's not entirely clear, even though we have the exponential function. So the complex inverse function theorem, if you look at it, looks just like what you'll find in your freshman calculus book about the real inverse function theorem. So if I have f which is analytic on it can be a small disk, and its derivative is not 0 at the center of that thing, so and f prime of a is not equal to 0, then like in the real case, the inverse to that function exists, at least locally, meaning then f inverse is well defined. So that means it's locally one-to-one, and it's well defined in a disk, a small disk perhaps, d sub epsilon about f sub a, and importantly, the inverse is analytic there. And the formula you learned in freshman calculus holds. So if I take d by dw of the inverse function, f inverse of w, that's equal to 1 over f prime of the f inverse of w. That's actually easy. That follows from the chain rule. Once you know the inverse exists and it has a complex derivative, then the chain rule is going to give us that famous formula. Let's see, I should make a remark here about the way oh, by the way, homework 3 is due tonight, and the exam is going to be in class, exam 1 and only, in class Wednesday, March 5th. Were there any questions about anything?
Homework is due tonight or tomorrow?
Yeah, not tonight. Thursday. Thanks. There's been some talk on Piazza you might find interesting about a couple of those problems. Let's see, maybe something I've been hinting at, but I never spelled out exactly. To make our lives easier so we can get to some famous results faster, it's convenient. In fact, lots of books that do complex analysis from sort of a computational point of view do this just to get things moving faster. I'm going to define, or the book likes to define, f being analytic means that the u and v are at least C1 smooth, to mean u and v are C1 smooth and satisfy the Cauchy-Riemann equations. All the functions we've encountered, like the exponential, polynomials, etc., have that feature. Then we know that the difference quotient f of z minus f of a over f over z minus a, then we know that that tends to a complex derivative. We showed all that stuff. In a fancier class, like the graduate version of this class, we only assume that the difference quotient exists. Analytic means the difference quotient goes to f prime of a on an open set. Okay, it's a fantastic fact that those two things are equivalent. But it's work to show that, and it's more of a philosophical work than anything, and it's not the kind of work that's useful from a sort of a engineering point of view. And so to save time, we'll assume we know this fact, that we can relax our assumptions about what it means to be analytic so we can get rolling. So these things are equivalent. And I posted a short paper I wrote on called something about Poisson and Dirichlet. I posted on the home page. At some point soon, it'll be very readable to you because I try to make it as elementary as possible. But it talks about this equivalence and the sort of philosophical reasons. It's fascinating. Anyway, I'm going to use the sort of wimp-out approach to the complex inverse function theorem just to make it quick and easy and obvious. So I'm going to be able to reduce it to the R2 version. So here we go with the C inverse function theorem. So here's the picture here. I've got this function which is analytic on a disk about A. I made it a disk of radius R. Okay, let me shade this in some weird color like yellow. Hopefully it's visible. Can you see that's kind of yellow? This yellow on yellow isn't very good. But that would map that disk. Here's f of A. So A goes to f of A. And that yellow blob would go to some kind of yellow blob around it. And in the proof of the R2 to R2 inverse function theorem, step one is to shrink down to a disk where the thing is 1-to-1. Let me make this f of A smaller. I'm going to shrink down to a disk of radius epsilon, so the yellow stuff goes through here. Okay, so that red dot is f of A, and this little disk has radius epsilon. Okay. And the fact is that's where f is going to be, the inverse is going to exist, and there'll be a 1-to-1 map. Now I'll shade this orange. Let's see. And then the inverse is going to exist on that orange blob. And it's going to map to a blob in here. Okay, and I'll call that blob U. That's the setup for the inverse function theorem. And so the fact is that F, this U is going to be an open connected set. So a domain. That means it's a domain. And F maps that thing one-to-one onto the disk of radius epsilon about F of A. And F inverse is analytic on that set. And it follows from the R2 to R2 version. Inverse function theorem. And that's because I like to write f of x plus iy equals u of xy plus iv of xy. And so whenever I have a complex function, there's a real mapping from R2 to R2. So xy gets mapped to u of xy, v of xy. And so we're assuming that u and v are C1 smooth. Because our Math 425 definition is that u and v are C1 smooth and satisfy the Cauchy-Riemann equations. So the R2 inverse function theorem at least tells us the differentiable inverse exists. Get inverse we get the inverse, let's see, that would be u, v, yeah. Okay, so here's the key. It's going to be that there's something special about the Jacobian matrix in the case of an analytic function. So the Jacobian matrix remember, is a thing. It's a matrix. I'll write it Jacobian matrix for the function defined by f. You take the gradient of u and put it in the first row. And then you take the gradient of v and put it in the second row. And if you think about what the Cauchy-Riemann equations mean, it means du dx is equal to v dy. And du dy is equal to minus dv dx. So there'd be a b here and a minus b here. Those are the Cauchy-Riemann equations. So that matrix has a special form. And in fact, when you think about it, remember in the real version of the inverse function theorem, the important thing was the determinant of the Jacobian matrix. That it needed to be an invertible matrix. And that happens when the determinant is non-zero. So the determinant is going to be, the determinant, when I do the Cauchy-Riemann equations, I would get du dx here, and I would get same number here. And then I'd get minus dv dx here, and minus that here. Oh, it's already there. I left that dv dx in the same spot. So what I did there, kind of like when I was messing around with why the Cauchy-Riemann equations are nice, that would turn that thing into complex multiplication back when it was in the numerator. That's exactly what I did. I turned all the y derivatives to x derivatives. And when you look at that, you get, so I've used the Cauchy-Riemann equations here. In a strategic way. When I do that, I get du dx squared minus a minus dv dx squared. That's plus. And the aha moment is that that's equal to the modulus squared of du dx plus I dv dx. And that's what was in red box number 1. I told you I was going to use that thing over that terminology for the rest of the course. That's red box number 1 for f prime, the derivative. And so this Jacobian determinant is f prime of z modulus squared. And if that's not 0, then we can use the inverse function theorem. So the Jacobian matrix, that's unequal to 0 at z equals a. So the hypothesis of the inverse function theorem is satisfied. That's the R2 to R2 version of the inverse function theorem. Holds. And so we get an inverse. We get an inverse function, which I'll use now in my complex notation. Let's write f equals capital U plus capital IV. And now remember the formula for the so here's what we think about. The Jacobian for the inverse, capital F. So capital F is equal to F inverse. That would be equal to d capital U dx. Let's see, I'm sorry. I don't want to do that yet. Remember the formula for the Jacobian matrix. It's the inverse of the Jacobian matrix of F. That's the R2 version. And so we're going to take the inverse of that matrix in the special form. And we saw this last time when I was messing around with, what was that thing? Oh, polar Cauchy-Riemann equations. That inverse is 1 over the determinant. So that's a squared plus b squared. And the inverse, you switch the diagonal elements.
Didn't you already switch the diagonal elements?
No, I didn't switch anything.
Isn't negative usually the number?
Oh, could be, yeah. So is that what I did last time?
Yeah.
Yeah, so let's do this. And then I would put it this way. So, using the famous formula for the 2 by 2 inverse, I take minuses in the other diagonal. And so we see the Cauchy-Riemann equations. So the Cauchy-Riemann equations for the Jacobian matrix means the inverse matrix is going to have the same property. And so that means that the inverse is analytic. So I've reduced the real version of the the complex version to the real version, and the Cauchy-Riemann equations. Questions about that? That sort of gets it over with quick and easy. Oh, and now the formula is just the chain rule. Because, let's see, I would have z is f inverse of f of z. And so, when I differentiate that with respect to z, I'd get 1 on the left is equal to f inverse prime of f of z times f prime of z. And so let's see if I want to get the formula in the form I have there. I would let this f of z be equal to a w. Then z would be equal to f inverse of z, f inverse of w, and check. That gives me the formula that everybody knows. By the way, now that I know this, I could have done this first, and then I could have seen that the log is analytic. So remark, I could have used this a couple days ago to see that whenever I have a branch of log of w is analytic. Because the derivative of the exponential is non-zero. So it would at least locally be locally differentiable, etc. And the problem then is making it defined, and that's what the business about choosing a branch is all about. So I could have used this to see log is analytic locally. Because d by dz of e to the z is itself, and e to the z is never 0. Okay, well that's kind of technical, so I'm going to do something that's not terribly technical. Now, were there any questions about the inverse function theorem? Here's a question. What the heck should I to the I be? I to the ith power. Well, back when you were studying the real exponential, you had a lesson in Math 161, probably, where you said, let's think about R to R. When you're trying to figure out what real powers meant, x to the n was an easy thing. You'd multiply x by itself n times. Okay, and then the next thing you would do is take x to the p over q was you'd take x to the pth power and then take the qth root of it. And let's see, that defines a power. So the big question was, in Math 161, what is something like pi to the square root of 2. Those are irrational numbers. Okay. Well, the picture in let's see, pi to the 0 is going to be 1. And, let's see, I need a really thin. That's going to be, the fact that we know what pi to the p over q is when p over q are rational means that we would have a whole bunch of points. And if I were to, these are the rational points. So the purple dots. And those are dense. The purple dots are rational points. Rational x values. Those are dense. So the thing would look like that. And if I were to scatter graph that, you say, oh my gosh, that's going to be a beautiful curve. And that turned out to be pi to the square root of 2, if you're going to make sense out of it, is, let's see, that would be e to the natural log of pi to the square root of 2. And that's equal to e to the square root of 2 log of pi. And so that's when we make a big deal about how wonderful the exponential function is, because you can express all real powers in terms of it. And so understanding just that one function means you understand all of them. Okay. Well, now we're going to do the same business in the complex case. So the complex version, let's think about it. All right, z to the w is going to be equal to e to the w log of z. But remember, my log of z thing is a set, so there's infinitely many values. So I'm using this notation to mean e to the w times, I'll use a zeta here, zeta, such that zeta is a log of z. There's infinitely many values of log in general. So it looks like in the complex case, it's kind of like the same problem we ran against when we were trying to cook up a log. Okay, and just like when we did log, there's going to be a preferred one. So a definition, the principal branch, the principal value of z to the w is equal to e to the w principal branch of log of z. And for example, things like the principal square root, an example, the principal nth root would would be, say, z to the 1 over n is equal to e to the 1 over n principal log of z. And for example, the principal square root, that would be a 1/2. Z to the 1/2 would be e to the 1/2 principal log of z. Let's see, let's think about this principal square root for a second. If I write r e to the I theta here, that would be e to the 1/2 natural log of r plus I theta. Where theta is between pi and plus pi, minus pi and plus pi, and we let plus pi win on the negative real axis. Okay, so let's think that's e to the 1/2 log r times e to the I theta over 2. Okay, that's the square root of r e to the I theta over 2. So if you think about what that does as a mapping, it sort of stretches the r direction, but on the theta direction and the theta business, it halves the angle. So the picture would be, as a mapping, let's see, I'm going to let here's the branch cut of the principal branch of log. It's going to close that like a fan, basically. So z squared, let's think about it. So the angle would go out to pi. When I half it, it goes from minus pi over 2 to plus pi over 2. So that means the mapping is going to go like this. And here's how I like to visualize this. This side, I'll make blue. That blue side, and that red line would get, because it's the special one, would get mapped up to that red line. And you get that feeling. And I'll make this side, what color? How about purple? This side would get the purple stuff. And this whole thing, you think of being a sheet of rubber, it would be like closing the fan. Okay, so here's the origin, and the origin would be there. Okay, so this direction is the square root of z direction, principal branch, and this direction, its inverse would be z squared. That'll be a useful map soon. Okay, some easy facts. Z to the n only has one value, even though it looks like, oh my gosh, I'm going to have infinitely many values. Only has one value. So it's the same old thing we're accustomed to. And that's easy to see because, let's see, z to the n is going to be e to the n log of z, and the logs of z are e to the n natural log of mod z plus I. Let's see, all the possible arguments are the principal argument plus 2n pi. So I'll put that plus 2n pi there, make that red. Okay, so I do the same thing I did last time and have e to the log z to the n would be nice. That's the easy thing. And this would be times e to the I arg z times e to the I 2n pi. Those are all 1. That's the point here. Even though it looks like, oh my gosh, I'm getting an infinite set here, these are all 1. This is 1. And so I get, I forgot my n here, e to the I. And so I only get 1. And it's the usual one. Let's see, is that, this would be, I'll leave the n down here. Anyway, you can convince yourself that's z times z times z. That would be e to the log z, e to the I arg z to the n, which is z to the n, which is z times z times z n times. So this new definition doesn't change anything about the old definition. And similarly, when you do the P over Q, the same kind of reasoning. Also, z to the P over Q, when those are rational, has Q values. Just like there's Q roots of unity. Okay, it's kind of fun to play around with these. And now let's think about I to the I. The principal value of I to the I is going to be e to the I principal log of I. That's e to the I, what is it? Natural log of mod I, that's log of 1, that's 0. And the principal argument of I is pi over 2. So this is 0 right here. And I get I times I is minus 1. How weird is this? The value of I to the I, the principal value, is e to the minus pi over 2. That's a real number. That's kind of feels weird. And now let's think about all the possible values. That would be e to the I, the set of all logs of I. And those would be e to the I, same old real part here. Once again, 0. But now I would get plus I times pi over 2 plus any multiple of 2n pi. Those are all the possible arguments of I. And so this time I would get e to the minus pi over 2 plus 2n pi. An infinite set of real numbers, and it's a weird infinite set, if you think about it. e to the minus pi over 2, that's some positive thing. And if those n's go to infinity, then I get e to the minus something gigantic. Those are going to go to 0. 0 is never going to get hit here, so I'll make it purple. But as n goes to infinity, those values are going to go down, 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 and they're going to be piling up at 0. So this is as n goes to infinity. Those dots sail into the origin and pile up there. And if n is negative, then I would start getting positive. The first one would be positive. And so those would be bigger than 1. E to the minus pi over 2 is less than 1. And after this, they'd start spreading out and heading off to infinity. So the dots would head off to infinity. As n goes to minus infinity. That's pretty weird. Infinitely many things with that weird behavior. Some of them can get arbitrarily close to 0, and I can get arbitrarily big. That's something weird. Anyway, that's just a fact of life in the complex domain, that when you're dealing with a complex inverse to the exponential, you're dealing with an infinite valued function. Yeah?
ln of I equals to 0, is that from the explicit definition, or is that just an identity?
The natural log of 1 is 0.
Yeah. But I guess if you took the 1/2 out to the front, it would be a negative 1, and that's an undefined number.
No, let's see, that's the log that goes there.
Is it just because it's 1 in the complex plane?
The natural log of 1 is 0. It's the modulus of I, yeah, so that I has unit modulus. Yeah, okay, that's what we're getting. Oh, let's see, I want to say a few words about section 3.4, about washers, wedges. It's a good thing to read, and we're going to use complex analysis to solve this kind of a problem. If you think about the steady state heat equation, it's the Laplace equation. So it would be du dt equals the Laplacian of u. And at steady state, things reach a steady state, and that derivative is 0. So that derivative would be identically 0 at what's called steady state, when you let the heat spread out and stabilize. And so the Laplace equations, the harmonic functions, solve heat problems. That's exciting. So what's the case of washers all about? The natural log of the modulus of r is locally the real part of a branch of the log function. And so it's harmonic, being the real part of an analytic function. Or you could calculate the Laplacian and say, sure enough, it is harmonic. That's the easy way to do it. And let's see, this would be the natural log of the r in polar coordinates. And so you realize, oh, that's an interesting heat problem. If I had, let's say I have a washer, which would be centered about something, and I'd have an outer radius, I'll call that capital R naught, and the inner radius would be little r naught. And the problem is to find a harmonic function that has certain values on those two circles. So the problem is find harmonic u with u equals T1 on the circle of radius r naught about 0. Let's let that red dot be the origin. And T2 on the circle of the small one. Those are circle C's for circles. Well, it turns out to be a really easy, let's see, so let's think about solutions. Log r is a solution to that, well, log r has some values on there. And then I could multiply log r by something. That would, I could change one of the values on the circles by multiplying by something. And if I want, that's not going to be enough. I'd get one circle I could do it, and the other circle I couldn't. But a times log r plus b, where these are constants, this one's going to work. And so, in fact, if you're going to make yourself solve that problem, you get two equations, namely a times log of little r naught plus b would be the T2, and a times log of the big r naught plus b, you'd want that to be T1. That's two equations and two unknowns. You can solve for the a and the b. And the solution then would be a times log mod z plus b. Let's see, kind of running out of time. Let me talk about wedges and walls. They're kind of equivalent. The key to this one is u equals the argument of z. Let's take the principal argument of z. That's the imaginary part of a complex log function. In fact, it's the imaginary part of the principal log function. Is harmonic. So if I wanted to find a solution to a heat problem that was at some temperature on the vertical and some temperature on the horizontal and harmonic on the inside, I would try, let's see, I'd get arg z. That wouldn't be enough. That would give me 0 on the bottom one and pi over 2 on the red one. So that wouldn't be enough. I could write a times arg z. I'd still get 0 on the bottom one, but then I could make the red one whatever I want. And so the brilliant thing is today a times arg z plus b. This is going to work. And you can do that in other geometries. For example, this geometry works just fine also. So this would be 0 right here. And I'd want the temperature to be T2 here and T1 here.